What if everything you see, hear, and touch is just a fraction of what truly exists? Imagine an entire universe brimming with dimensions we can't perceive right here, right now. Get ready to have your mind expanded as we journey beyond our five senses to explore the unseen layers of reality. Welcome to the Unseener Perception of the World is a carefully curated experience, a masterpiece of biological engineering designed to help us navigate our environment and survive. We trust our senses implicitly, believing that what we see, hear, and touch is a faithful representation of reality. But what if this perception is more of a convenient illusion than an objective truth? What if our senses are not windows to the world, but rather filters, carefully selecting and processing a sliver of the vast, unseen reality that surrounds us? Consider the electromagnetic spectrum, a continuous range of radiation that encompasses everything from radio waves to gamma rays. Our eyes, for all their intricate beauty, can only detect a minuscule portion of this spectrum, a narrow band we call visible light. We are blind to the radio waves that carry our communications, the microwaves that heat our food, the infrared radiation that emanates from all warm objects, the ultraviolet light that can damage our skin, and the X-rays and gamma rays that are so energetic they can pass through solid matter. These are not theoretical constructs, they are as real as the light we see, yet they remain invisible to our unaided senses. Our world is bathed in a sea of light that we cannot perceive. Similarly, our ears are tuned to a specific range of sound frequencies. We can hear the gentle rustle of leaves and the roar of a jet engine, but we are deaf to the low-frequency rumbles of infrasound, which can be generated by earthquakes and volcanic eruptions, and the high-frequency chirps of ultrasound, used by bats and dolphins for echolocation. These sounds are not silent, they are simply outside the range of our biological hearing. Our reality is a symphony of sounds, but we can only hear a few notes. This brings us to a profound question. What is the difference between reality and our reality? Is there an objective, external world that exists independently of our perception, or is reality a subjective experience shaped and molded by the limitations of our senses and the interpretive power of our brains? Neuroscientists like Donald Hoffman have proposed a fascinating and provocative idea: that our perception of reality is not a veridical representation of the world, but rather a user interface, a set of simplified icons and symbols that guide our actions and help us survive. Just as a computer desktop with its folders and files is a simplified representation of the complex inner workings of the machine, our perceived reality is a simplified representation of a much deeper, more complex underlying reality. This interface theory of perception suggests that our brains have evolved to filter out the vast majority of information from the external world, presenting us with only what is necessary for our survival and reproduction. This is a powerful and efficient strategy, but it also means that we are living in a self-imposed perceptual prison, a world of our own making. We are like actors on a stage, unaware of the vast, unseen backstage machinery that makes the play possible. But what if we could peek behind the curtain? What if we could transcend the limitations of our senses and explore the hidden layers of reality? This is the tantalizing promise of modern physics, which suggests that our familiar three-dimensional world may be just a small part of a much larger, more complex reality, a multiverse of unseen dimensions and parallel worlds. The journey into this unseen realm is not for the faint of heart, for it will challenge our most cherished beliefs about the nature of reality and our place in the cosmos. But for those who are willing to take the leap, the rewards are immeasurable. A deeper understanding of the universe, a new appreciation for the mysteries of existence, and a glimpse into the mind-bending possibilities that lie beyond our familiar 3D world. The scientific search for hidden dimensions for centuries, humanity has grappled with the fundamental nature of reality. Our scientific endeavors, from the macroscopic dance of planets to the microscopic ballet of atoms, have consistently revealed a universe far more intricate and profound than our immediate senses suggest. Yet, even with our most powerful telescopes, and microscopes, we remain tethered to the familiar three spatial dimensions. But what if these are not the only dimensions? What if the universe is woven with extra, hidden dimensions too subtle for our direct perception, yet profoundly influencing the fabric of reality? This is the audacious proposition at the heart of modern theoretical physics, particularly in the realm of string theory and M-theory. Imagine, for a moment, that the fundamental building blocks of our universe are not point-like particles, as once thought, but rather infinitesimally small, one-dimensional vibrating strings. Just as the vibrations of a violin string produce different musical notes, the different vibrational modes of these fundamental strings give rise to the diverse array of particles and forces we observe in the universe. The elegance of string theory lies in its potential to unify all fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces into a single, coherent framework. However, for string theory to be mathematically consistent, it requires the existence of extraspatial dimensions beyond the three we experience daily. While our everyday intuition struggles to grasp the concept of more than three spatial dimensions, string theory typically postulates 10 dimensions in total. These additional dimensions are not vast, expansive realms like our familiar length, width, and height. Instead, they are thought to be curled up or compactified into incredibly tiny, unobservable spaces. Think of a garden hose. From a distance, it appears to be a one-dimensional line. But if you were an ant walking on its surface, you would discover a second, curled-up dimension: its circumference. Similarly, these extra dimensions are believed to be so tightly curled that they are imperceptible to our current experimental methods. Perhaps on the order of the Planck length, an unimaginably small scale of y-35 meters, M-theory takes this concept a step further. It emerged as a unifying framework for all 5 consistent superstring theories, operating in an even higher dimensional space of 11 dimensions. The additional dimension in M-theory provides a deeper understanding of the relationships between the various string theories, suggesting they are all different facets of a single, more fundamental theory. The existence of these extra dimensions is not merely a mathematical curiosity. It is crucial for the internal consistency of these theories and offers a tantalizing path towards a theory of everything that could reconcile the seemingly disparate realms of quantum mechanics and general relativity. The idea of hidden dimensions is not entirely new. Nearly a century ago, in the 1920s, the mathematicians Theodor Kaluza and Oscar Klein independently explored a similar concept in what became known as Kaluza-Klein theory. Kaluza proposed a revolutionary idea that if the universe possessed an extra, fifth spatial dimension, then Einstein's theory of general relativity, when extended to 5 dimensions, would naturally yield both general relativity describing gravity and Maxwell's equations describing electromagnetism when projected down to our familiar 4-dimensional spacetime. Klein later refined this idea, suggesting that this 5th dimension was not expansive but rather curled up into a tiny, unobservable circle. This compactification explained why we don't perceive this extra dimension directly, any movement within it would quickly bring one back to the starting point, much like walking around a tiny, invisible loop. The implications of these curled-up dimensions are profound. Even though we cannot directly observe them, their existence could profoundly influence the fundamental forces and particles that govern our universe. The way these dimensions are curled up, their specific geometry and topology, could determine the very nature of the particles we observe and the strengths of the forces they experience. It's akin to the subtle differences in the shape of a musical instrument influencing the timbre and resonance of the notes it produces. The universe, in this view, is a symphony played on a multi-dimensional instrument, with the hidden dimensions providing the intricate structure that shapes the cosmic melody. The scientific search for these hidden dimensions continues, pushing the boundaries of our understanding and offering a glimpse into a reality far richer and more complex than we ever imagined. Beyond space, exploring time and consciousness. journey into the unseen layers of reality extends beyond the spatial dimensions, venturing into the enigmatic realms of time and consciousness. For centuries, time was perceived as a linear, immutable flow, a universal clock ticking uniformly for everyone. However, Albert Einstein's revolutionary theories of relativity shattered this Newtonian view, revealing time as the fourth dimension, inextricably woven with the three spatial dimensions to form a unified fabric known as spacetime. In this four-dimensional spacetime continuum, every event in the universe can be precisely located by its three spatial coordinates: length, width, height, and one temporal coordinate: time. We are not merely moving through space, we are constantly traversing spacetime. The implications of this are profound. Just as we can move forward and backward, left and right, up and down in space, our movement through time is also a fundamental aspect of our existence. However, unlike spatial dimensions where we can freely choose our direction, our journey through time appears to be unidirectional, always moving forward. Yet, the theoretical possibility of time travel, particularly to the future, is a direct consequence of Einstein's theories. Special relativity predicts that time can dilate or slow down for objects moving at speeds approaching the speed of light. If you were to travel in a spaceship at near light speed for a period, you would age less than those who remained on Earth, effectively traveling into their future. General relativity, which describes gravity as the curvature of spacetime, suggests that strong gravitational fields can also cause time to slow down. This means that near massive objects like black holes, time would pass more slowly than in regions of weaker gravity. While these forms of time travel to the future are theoretically sound, traveling to the past remains a far more speculative and problematic concept, often requiring exotic phenomena like wormholes or cosmic strings, and grappling with paradoxes such as the grandfather paradox beyond the physical dimensions of spacetime. Some theories delve into the even more elusive concept of higher dimensional consciousness or alternative states of awareness. This is where physics, philosophy, and even spirituality begin to intertwine. The idea is that our conventional, waking consciousness might be just one limited manifestation of a broader, more expansive awareness that exists in dimensions beyond our immediate grasp. Our brains, in this view, might act as a kind of receiver or filter, processing a fraction of this larger consciousness into our individual subjective experience. Proponents of this idea suggest that altered states of consciousness induced through practices like deep meditation, lucid dreaming, psychedelic experiences, or even intense emotional states could offer fleeting glimpses into these higher dimensions of awareness. In these states, the usual boundaries of our perception might dissolve, allowing for a more direct connection to a reality that is typically veiled by our everyday sensory filters. While scientific validation for such claims is still in its nascent stages, these concepts encourage us to question the very nature of our subjective experience and consider that our minds might be capable of perceiving far more than we currently realize. This leads to one of the most mind-bending questions of all. Is our perception of reality a form of a cosmic simulation? The simulation hypothesis, popularized by philosopher Nick Bostrom, proposes that our entire universe, including our consciousness and all our experiences, could be an elaborate computer simulation created by a technologically advanced civilization. The argument is based on probabilities. If it's possible for a civilization to reach a post-human stage with immense computing power, they would likely run numerous simulations of their ancestral past. Given the vast number of potential simulated realities compared to a single base reality, the statistical likelihood that we are living in a simulation becomes significant. While this remains a hypothesis, it challenges our fundamental assumptions about reality. If our universe is a simulation, then the laws of physics might be akin to lines of code, and anomalies or unexplained phenomena could be glitches in the matrix. This idea, while seemingly plucked from science fiction, has gained traction among some physicists and philosophers, prompting serious discussions about how one might even begin to test such a proposition. Whether a simulation or not, the very act of contemplating such possibilities forces us to confront the profound mystery of existence and the potential for reality to be far more intricate and layered than our current understanding allows. Parallel realities and the multiverse concept of a single, solitary universe, once a cornerstone of cosmological thought, is increasingly being challenged by scientific theories that suggest our cosmos might be just one of an infinite number of parallel realities, collectively forming a grander structure known as the multiverse. This mind-bending idea, once relegated to the realm of science fiction, is now a serious area of inquiry for physicists and cosmologists. One of the most compelling and controversial interpretations that gives rise to the multiverse is the many worlds interpretation (MWI) of quantum mechanics. Quantum mechanics, the theory that governs the behavior of matter and energy at the atomic and subatomic levels, is famously strange. It tells us that particles can exist in multiple states simultaneously, superposition until they are observed, at which point they collapse into a single, definite state. This measurement problem has puzzled physicists for decades. MWI, first proposed by Hugh Everett III in 1957, offers a radical solution: there is no collapse. Instead, every time a quantum measurement is made, or indeed every time a quantum event with multiple possible outcomes occurs, the universe itself splits into multiple, parallel universes. In each of these new universes, a different outcome of the quantum event is realized. For instance, if a quantum particle has a 50% chance of being in state A and a 50% chance of being in state B, then upon measurement, the universe doesn't just choose one state. Instead, the universe branches, creating one universe where the particle is in state A and another where it is in state B, and in each of these universes, there's a version of you observing that particular outcome. This means that with every decision you make, every coin you flip, every quantum fluctuation that occurs, the universe is constantly branching, creating an unimaginably vast, perhaps infinite, number of parallel realities. In one universe, you chose coffee; in another, tea. In one, you took that job; in another, you didn't. This interpretation suggests that all possible outcomes of every event are not just theoretical possibilities but actual realities playing out in their own separate universes. While MWI is still a subject of intense debate and lacks direct experimental verification, it provides a compelling, if unsettling, picture of a constantly expanding multiverse where every conceivable possibility is realized. Another powerful theoretical framework that points towards a multiverse is the inflationary cosmology theory, particularly its extension into eternal inflation. The standard Big Bang model describes the universe's expansion from an extremely hot, dense state. However, it struggles to explain certain observed features, such as the remarkable uniformity and flatness of our universe. To address these issues, the theory of cosmic inflation was proposed, suggesting that the universe underwent a period of extremely rapid, exponential expansion in the first tiny fraction of a second after the Big Bang. This inflationary epoch smoothed out irregularities and stretched the universe to its observed flatness. Eternal inflation takes this concept further. It posits that inflation, once it begins, does not necessarily end everywhere simultaneously. Instead, it continues indefinitely in some regions, while in other regions it slows down and stops, forming bubbles of spacetime. Each of these bubbles then expands to become a separate, self-contained universe. Our own universe, in this scenario, would be just one such bubble in a vast, ever-inflating multiverse foam. These bubble universes could be incredibly diverse, with different physical laws, fundamental constants, and even different numbers of dimensions. Some might be barren and empty, others teeming with life, and still others governed by physics entirely alien to our understanding. The implications of these infinite possibilities are truly mind-bending. If the multiverse is real, then every conceivable scenario, no matter how improbable, is playing out somewhere. There could be universes where dinosaurs never went extinct, where humans evolved with wings, or where the laws of physics are so different that matter itself behaves in unimaginable ways. This perspective challenges our anthropocentric view of the cosmos, suggesting that our universe, with its specific laws and conditions that allow for life, might not be unique or specially tuned, but rather just one outcome among an infinite ensemble. The multiverse, in this sense, offers a solution to the fine-tuning problem, the observation that the fundamental constants of our universe seem perfectly calibrated for the existence of life. If there are infinite universes with varying constants, then it's not surprising that at least one of them would have the right conditions for life to emerge. We simply happen to reside in one such universe. Exploring the mind-bending implications of infinite possibilities forces us to reconsider our place in the cosmos. Are we truly unique, or are there countless versions of ourselves living out different lives in parallel realities? While these ideas remain theoretical, they push the boundaries of scientific inquiry and inspire us to imagine a reality far grander and more complex than we ever dared to dream. The practical implications and future exploration of extra dimensions and the multiverse is not merely an academic exercise in theoretical physics. It holds the potential to profoundly reshape our understanding of the universe and, in the long term, revolutionize technology. While direct interaction with these hidden dimensions remains firmly in the realm of speculation, the theoretical frameworks that posit their existence offer tantalizing glimpses into possibilities that could transcend our current technological limitations. Imagine a future where our understanding of these dimensions allows us to manipulate the very fabric of space-time. This could lead to breakthroughs in energy generation, perhaps by tapping into previously inaccessible energy sources or by harnessing the energy from other universes. The concept of faster-than-light travel, a staple of science fiction, might become a reality if we could find ways to create shortcuts through higher dimensions, bypassing the cosmic speed limit imposed by our familiar four-dimensional space-time. Similarly, communication across vast cosmic distances could be instantaneous if signals could traverse these extra dimensions. In the realm of materials science, a deeper understanding of how curled-up dimensions influence fundamental forces could lead to the creation of novel materials with extraordinary properties. Materials that are incredibly strong yet impossibly light, or those with unprecedented conductive or insulating capabilities, might emerge from such knowledge. Furthermore, if the simulation hypothesis holds any truth, then understanding the underlying code of our reality could grant us unprecedented control over our environment, allowing for feats that currently seem miraculous. Beyond technological advancements, the pursuit of these theories pushes the boundaries of our fundamental understanding of the universe. The unification of gravity with other fundamental forces, a long-standing goal in physics, might only be achievable within a framework that includes extra dimensions. Mysteries like dark matter and dark energy, which constitute the vast majority of the universe's mass and energy but remain elusive, could find their explanations in the interactions with these hidden dimensions or other universes. The very nature of consciousness and reality itself could be re-evaluated, leading to a more holistic and interconnected view of existence. But how do we move from theoretical constructs to empirical evidence? The search for these hidden dimensions and parallel universes is an ongoing endeavor, with scientists employing cutting-edge experiments and observational efforts. The Laser Interferometer Gravitational Wave Observatory LIGO, for instance, has opened a new window into the universe by detecting gravitational waves ripples in spacetime caused by cataclysmic cosmic events like merging black holes and neutron stars. While LIGO is not designed to directly detect extra dimensions, it provides a powerful tool for probing the fundamental nature of spacetime. Future gravitational wave observatories with increased sensitivity might be able to detect subtle anomalies or signatures in gravitational waves that could hint at the presence of extra dimensions or interactions with other universes. Particle accelerators, such as the Large Hadron Collider LHC at CERN, are at the forefront of the experimental search for extra dimensions. By smashing particles together at energies never before achieved, physicists hope to create conditions where extra dimensions might briefly manifest. If these dimensions exist, they could affect the way particles interact or even allow for the production of new, exotic particles that can only exist in higher dimensional spaces. For example, if gravitons, the hypothetical particles that mediate gravity, can escape into extra dimensions, it could explain why gravity is so much weaker than other fundamental forces. The search for missing energy in particle collisions, which could indicate particles escaping into extra dimensions, is one of the key experimental signatures scientists are looking for. While no definitive evidence for extra dimensions or the multiverse has been found yet, these experiments continue to push the boundaries of our understanding. They provide crucial data that constrains theoretical models, ruling out some possibilities and refining others. The absence of evidence is not evidence of absence, and the sheer scale and complexity of these phenomena mean that their detection might require even more advanced technologies and innovative experimental designs. Ultimately, the exploration of multiverse theories and hidden dimensions is a testament to humanity's insatiable curiosity and our relentless quest to understand our place in the cosmos. It is a call to ponder the vastness of existence, to embrace the unknown, and to recognize that our current understanding of reality might be just the beginning of an endless frontier of discovery. The universe, in all its multidimensional glory, awaits our further exploration, promising a future where the boundaries of what we perceive as real are constantly being expanded and the mind-bending possibilities of infinite realities continue to inspire and challenge us.